Now to the next problem. Prove that cos 6 theta plus sin 6 theta is equal to 1 minus 3 sin square theta cos square theta. We start with LHS. Now we have cos 6 theta. We write that as cos square theta the whole cubed, and sin 6 theta we write it as sin square theta the whole cube. Now this is of the type a cube plus b cube. We write the formula for this as a plus b into a square minus ab plus b square. So we get cos square theta plus sin square theta into cos 4 theta minus cos square theta sin square theta plus sin 4 theta. Now the first bracket, cos square theta plus sin square theta gives us 1, which is the identity. Now from the second bracket, we write cos 4 theta as cos square theta the whole square. Now why are we doing this? We want to try and get everything in terms of one trigonometric ratios. That is, we want to write everything in terms of sin theta. So we will write cos 4 theta as cos square square and then later on convert this to sin. Now the second term, cos square theta into sin square theta. The cos square theta we replace by 1 minus sin square theta, and the third term as it is. So we have 1 minus sin square theta the whole square minus 1 minus sin square theta into sin square theta plus sin 4 theta. Now we simplify this further as 1 minus 2 sin square theta plus sin 4 theta. Now we open up the bracket there, we get minus sin square theta plus sin 4 theta and sin 4 theta as it is, which is simplified further as 1 minus 3 sin square theta plus 3 sin 4 theta. Now from the last two terms, we can remove minus 3 outside. We have minus 3 sin square theta into 1 minus sin square theta. Now 1 minus sin square theta can be replaced by cos square theta. So we get the LHS as 1 minus 3 sin square theta into cos square theta, which is nothing but our RHS. So we have proved LHS and RHS equal. Next problem, prove that sin theta plus cosec theta the whole square plus cos theta plus sec theta the whole square is equal to 7 plus tan square theta plus cot square theta. Here in LHS, we have sin, cos, cosec and sec, whereas in RHS we have tan and cot. Now we want to get rid of sin and cos from the LHS, and we can write cosec and sec in terms of cot and tan. Before doing that, first let's expand the LHS as sin theta plus cosec theta the whole square can be written as sin square theta plus 2 sin theta into cosec theta plus cosec square theta. Now the second bracket, cos theta plus sec theta the whole square becomes cos square theta plus 2 cos theta sec theta plus sec square theta. Now sin square theta plus cos square theta is 1. 2 sine theta into cosec theta will give us 2, because sine theta and cosec theta are the reciprocals of each other. Similarly, 2 cos theta sec theta will give us 2, because cos and sec are the reciprocals of each other. Now, cosec square theta can be replaced in terms of cot as 1 plus cot square theta, that is the identity, and we replace sec square theta as 1 plus tan square theta. So, we have 1 plus 2 plus 1 plus 2 plus 1 plus tan square theta plus cot square theta. That is 7 plus tan square theta plus cot square theta, which is our RHS. So, we have proved LHS equal to RHS. Here's the next problem. Prove that sin square theta plus cos 4 theta equals cos square theta plus sin 4 theta. Here in the LHS we have sin and cos, and same way in RHS we have sin and cos, but with different powers. So we will start with LHS, which is sin square theta plus cos 4 theta. Now we want to simplify this, so we write cos 4 theta in terms of sine. So we write cos 4 theta as cos square theta the whole square. Then substitute that cos square theta as 1 minus sin square theta, because of the identity sin square theta plus cos square theta is equal to 1. So we get sin square theta plus 1 minus sin square theta the whole square. We expand this as 1 minus 2 sin square theta plus sin raised to 4 theta. So we get 1 plus sin square theta minus 2 sin square theta gives us minus sin square theta plus sin raised to 4 theta. Now, what is 1 minus sin square theta? That is cos square theta plus sin raised to 4 theta. So, LHS is equal to RHS proved. Now to the next problem. If x is equal to r sin a cos b, y is equal to r sin a sin b, and z is equal to r cos a. To prove that x square plus y square plus z square is equal to r square. Same way we start with LHS and we substitute x, y and z with the given values. We get r sin a cos b the whole square plus r sin a sin b the whole square plus r cos a the whole square. Now open up the brackets, but before that we have r common throughout, which is under the square sign. Remove that outside, we get r square into sin square a cos square b plus sin square a sin square b plus cos square a. Now we want to simplify this, so we write cos in terms of sin. So from the first term we have sin square a into 1 minus sin square b. Second term as it is. The third term we replace as 1 minus sin square a. Now simplify sin square a minus sin square a sin square b plus sin square a sin square b plus 1 minus sin square a. Now we cancel sin square a and we cancel minus sin square a sin square b. So in the bracket we are left with 1. So we have r square into 1, which is r square. So we have proved LHS and RHS equal. Next problem, prove that root 1 minus cos A upon 1 plus cos A is equal to sin A upon 1 plus cos A. Now here in LHS we have the square root sign, but in the numerator we have 1 minus cos A and denominator 1 plus cos A. Now what comes to your mind? We must rationalize the denominator. But if you see the denominator in left side is 1 plus cos A, it's the same in right side also. So do not rationalize the denominator here. In fact, in the numerator we have 1 minus cos A, which becomes sin A in the RHS. So we must rationalize the numerator, that is multiply them by 1 plus cos A. So we get root 1 minus cos A into 1 plus cos A upon 1 plus cos A into 1 plus cos A. The numerator becomes 1 minus cos square A, which is nothing but sin square A, because of the identity sin square A plus cos square A equal to 1. Now the denominator becomes 1 plus cos A the whole square. Now we write this as sin A upon 1 plus cos A the whole square under the root sign. Now we cancel the root and the square sign. We are left with sin A upon 1 plus cos A, which is our RHS. So we have proved LHS and RHS equal.
Got it.
Now let's look at a little different problem. Here we are given 3 sides. We want to prove them equal. We start with the first side. In this, the numerator of the first term is the same as the denominator of the second term and vice versa. So the best possible method here is to take the LCM as sin A minus cos A into sin A plus cos A. So the numerator becomes sin A plus cos A the whole square plus sin A minus cos A the whole square upon sin A minus cos A into sin A plus cos A. Now we expand the numerator as sin square A plus 2 sin A cos A plus cos square A plus sin square A minus 2 sin A cos A plus cos square A. Denominator will become sin square A minus cos square A. Now from the numerator, sin square A plus cos square A is 1, the identity, and we have 2 sin A cos A minus 2 sin A cos A, they cancel. So we are left with 1 plus 1, which is 2 in the numerator, denominator as it is sin square A minus cos square A. So we have got LHS as 2 upon sin square A minus cos square A, which is nothing but our second side. Now we have the third side. If you look there, we do not have the cos square term in the third side. So we replace cos square A as 1 minus sin square A. We get 2 upon sin square A minus 1 minus sine square a. So the denominator becomes sine square a minus 1 plus sine square, which is simplified as 2 sine square minus 1. So we get the third side, which is 2 upon 2 sine square minus 1. So we have proved that these three sides are equal. Here's the next problem. This is very interesting. Now in LHS we are given tan A plus sec A minus 1 upon tan A minus sec A plus 1. In RHS we have 1 plus sin A upon cos A. We obviously want to prove them to be equal. Now in LHS we have tan and sec, and in RHS sin and cos. Now what comes to your mind? That we must substitute tan in terms of sin and cos, and same way sec in terms of cos. But that method is not going to work very well here. In this, we need to replace 1 in the numerator as sec square A minus tan square A. This is because of the identity 1 plus tan square A is equal to sec square A. Right now, we are just substituting 1 in the numerator, denominator as it is. Now let's do that. That part, sec square A minus tan square A, can be simplified as sec A minus tan A into sec A plus tan A, denominator as it is. So we can remove tan A plus sec A common. We'll be left with 1 minus, in the bracket, sec A minus tan A, denominator as it is. Now we rearrange the terms of the bracket as tan A minus sec A plus 1. This bracket is nothing but the denominator, so we cancel. We are left with tan A plus sec A. Now tan A can be written as sin A upon cos A and sec A as 1 upon cos A, which can be simplified as sin A plus 1 upon cos A. Rearrange the terms, we get 1 plus sin A upon cos A, which is nothing but our RHS. So we have proved LHS equals RHS. Now note here, in this you will have to substitute 1 in the numerator as sec square A minus tan square A. Do not substitute in the denominator. If you do so, you will not get the answer.